Energy is just power times time. It's given the units are watt hours, but I'd say always, I'll be safe and say usually, but I think almost always it's kilowatt hours that you're going to see. So you're going to use that K prefix, and it has to be the same number, of course. So, but yeah, it's going to be watt hours, and then I guess divide by 1,000 to get the K in there. It's um, It's a combination of power and time. Maybe an example would be if we took that powerful car example from when we were explaining power. So remember we said your car is probably powerful if it can go fast and uphill at the same time. That might implicate some power. And the question might be, I have a powerful car, it can do that. It can go fast uphill. So does it use a lot of energy? And the answer to that is, depends. You have a powerful car, did you just go up the hill one time? Or were you going up the hill all day long? And if you were going up all day long, yes, it used a lot more energy than if you just went uphill once. So it's that element of time, power with the over time is what gets you a high amount of energy. Maybe again, another example, I think you get it, but if you were chopping wood, you could say that it's very powerful if you're able to use that axe and chop a piece of wood in half, with one swing of the axe. So that's power. Are you using a lot of energy? Again, it depends. Did you just chop one piece of wood, or were you chopping wood all day long? And if you're chopping wood all day long with those powerful strokes, you're using a lot of energy. So power times time. Efficiency is a comparison of power out to power in. So efficiency is just asking the question, how much do you get out of a system compared to how much you put in? I mean, if you get everything out that you put in, that means you didn't lose anything, and that would be 100% efficient. And there is no possibility of that. There's always some loss in any system. So, but you would hope that you could get as much out as you can of a system when you compare it to what you have to put into it. So you strive for high efficiency that way. Whatever you lose, that's what makes it less than 100% efficient. The symbol for efficiency is this symbol here. Efficiency, it's always expressed as a percent. So when you take your answer, when you do the power out, compare it to the power in, it's a ratio. You just divide power out divided by power in. Then you're going to multiply it by 100. And that's what's going to be your answer. So it's always expressed as a percent. So now if we kind of take an overview of what we know from the beginning fundamentals, we can look here. Charge is coulombs at a point or place. And that comes from the imbalance of electrons and protons. I mean, if you have an equal number of electrons to protons, if they're the same number, protons and electrons, you'll have a neutral atom. But when you have more electrons than protons in a place, you would have a negative charge. If you have less electrons than protons, you're missing some electrons, then you'd have a positive charge at that place. So, but charge, it has to do with how many coulombs. That's a real high number. Remember, that's that cup of electrons. That's what a coulomb is. If you remember, it's a really high number. You can look that up. I'm trying to remember myself. You don't have to memorize that number. I'm going to take a stab at it. 6.25 times 10 to the 18th electrons, perhaps, or that many electrons missing in comparison to protons. Yeah, you can't, incidentally, move protons out of an atom or if you do, I mean, you're talking nuclear manipulation there. You're at the nucleus, and I shouldn't say you can't, but I mean, if you do, that's nuclear reactions. Well, let's see, taking neutrons in and out. I'm off track here, but if you could change the number of protons, because some people are curious, like we fool around with the electrons. We take electrons away, we add electrons to an atom, and you know, we do that a lot with electricity. If you were able to add or take away protons, you could change the element itself. You know, so alchemists were always in pursuit of that. And I have to remember again, I don't have the atomic chart memorized or right next to me, but is it lead perhaps that sits next to gold? I'm going to hazard a guess again, but whatever element sits next to gold, if it was deficient by one proton, which that might be lead, and you add a proton to it, presto, you have gold now. You've changed the element. So changing protons, you know, pushing protons around would let you change elements. We don't really know how to do that, I don't think. Okay. So anyway, got off track there. But charge, coulombs, is the coulombs at a point or place that you have sitting there. And it can be a static charge. You can get high charge real easily. Like we said before, static electricity is a good example. You can, you know, scrape, lots of ways you can get electrons piled up or removed. Friction, for example, just rub a balloon in your hair. Okay, back to the list. But voltage then is really the difference in charge between 2 points, and it's always good to stress that it's 2 points when you're talking about voltage. You can't say you have a voltage here or there, you know, pointing to a single point. You always want to really have that in your mind, that when you say you have a voltage, you're talking about a difference between 2 points. So 5 volts doesn't mean just 5 volts sitting on a point somewhere. But it means 5 volts difference between 2 points. And many times one of those points might be circuit common, so we don't always mention it. But yes, voltage is always the difference between 2 points. And current, that's the flow. It's the flow of the charge. So you can see how we're building this list up. I mean, we're defining charge. Voltage is a difference in charge between 2 points. Current is the flow of charge that's happening. You can think of flow as in how many coulombs flow past a given point for a given time. So, of course, for the ampere, it's 1 coulomb per second is equal to 1 amp. So again, it does keep going back to this coulombs thing, doesn't it? Or charge, right? So it all starts with charge. You know, piling up charge at a point, and then a difference between 2 points is the voltage, and the flow of the charge. That would happen, of course, if you have the difference here. You need a difference. First of all, you need an imbalance that wants to equalize. And then what do you need? Can you remember? You need a path. So if you have the imbalance that wants to equalize, and then you provide a path, you'll get current flowing. And of course, we know Ohm's law tells us that simple relationship between the imbalance that wants to equalize, the path you provide, that can be some amount of conductance or resistance, you know, will give you a certain amount of current. So that's that V over R. If I negate, we'll scribble that out for a little bit. There's 2 ways of talking about it: glass half empty, glass half full. So given a certain voltage and a path with a certain resistance, you'll get this current. Yep. And that's the flow. And then we can talk about power as really a combination of voltage and current. You know, if you need both to have power. I mean, you could have high voltage, again, that 30,000 volts you generated with the balloon rubbing it in your hair doesn't mean you generated a lot of power, because there really is not much current at all. In fact, if it's a static voltage, there's no current. So there's not much power there. You didn't create or generate power, you just generated voltage. And likewise, if you have current that you generated through a very low resistive path, it was very easy to flow. So there's really not much power there. So it's possible to have voltage and low current and not much power, like high voltage, low current, and not much power. That's possible. It's possible to have high current and low voltage and not much power. But if you have a decent amount of both, or whatever the amount of both you have, that determines the power. So power is the combination, meaning you have voltage and current, and whatever that combination is, that tells you how much power. Okay. And then you have energy, which is really taking whatever power you have and then asking the question, for how long, right? Time. So maybe you have lots of power, but for how long was it used? And that tells you how much energy was used. Okay. And then another, finally, that we learned is the efficiency, and that's really comparing how much, if you put some power in, right, how much did you get out? If you get, and like we said, if you get everything out that you put in, well, that would be 100%. That's not possible. Every system has losses, and so to look at that with a number, we'll take and compare the output with the input simply by dividing output divided by input, and then multiplying by 100 so that we have it as a percent. And then we'll tell ourselves it's not 100% efficient, but what is it? 90% efficient? You know, that means I could, you know, put 10 units in and get 9 units out. That'd be 90% efficient. Or whatever the efficiency is, but it's always given as a percent. So, okay.